Hi, welcome back. We're talking about Smith charts and transmission lines. And I've got an example here. This is the first of two examples that I have on the Smith charts. And the Smith chart is kind of tricky for me to do electronically because of the chart itself. And so I'm just going to walk you through my PDF of notes. So everything is already written. So you'll need a Smith chart, which you can get from Wikipedia. I've got the link here, and then you also need a ruler. So let's work through it. So for example, a lossless transmission line with characteristic impedance 50 ohms is 30 meters long and operates at 2 megahertz. The line is terminated with a load given by this thing 60 plus J40 ohms. And then if u, the speed of the wave, is 0.6 c on the line, c is the speed of light, use a Smith chart to approximate, and we're going to approximate these things: the reflection coefficient, the Viswar, and the voltage standing wave ratio, and the input impedance. And I say approximate here because that's what you can do on Smith charts. You're approximating because you're taking measurements, and your measurements are only so accurate, up to a certain point. All right, so the first thing we need to do is normalize the load impedance. If you remember, the Smith chart is for normalized loads, so that we can use the same Smith chart for every situation, every line. So what we do is we take the load impedance, which was 60 plus J40, and we divide it by the characteristic impedance of the line, which in this case is 50. And so when you do that division, you get 1.2 plus J 0.8. So that's the normalized load impedance. And so now we can find this point on the Smith chart. So let me do that. That's point P. So I'll just show you there. So here's point P in red. And why is that, where I say it is? Well, that's 1.2. You see the 1.2 right there? That's 1.2 on the R circle. It's 1.2, and then so we follow the R circle around 1.2, and then that meets the 0.8 X circle, right? And so that is the point P right there. And so what I've done here is I found the origin first of all, and then so once I'm at the origin, I've connected, using a straight edge, the points 0 and P. So, and I've labeled that, this ray 0P. And then I've also extended it with the dotted red line all the way out here to the edge of the Smith chart, and I've labeled that point P prime. Okay, and I've labeled that ray 0, or not 0, OP prime, right? So I've got some angles here, which I'll talk about in a second, but for right now we need to be worried about these rays and these points O and P. Okay, so now that I've got that point P, I've done this exactly. I've drawn those lines, and what you have to understand here is that this is a a scaled version. So I can zoom in and zoom out, and so your measurements are going to be different than my measurements depending on how much you've zoomed, and if you've downloaded the Smith chart, what your resolution was, and all of this. And so when I did this by hand, I measured from O to P prime. And the reason I did that is because if you recall, everything on the Smith chart, everything on the outer edge of the Smith chart, that is, corresponds to a reflection coefficient whose magnitude is 1, right? Think about how the Smith chart was constructed. That's a magnitude of 1. It's kind of like the unit circle, if you want to think of it like that. And so I've measured the distance from O to P prime, and in this case, when I did the measurement, I got 7.1 centimeters. Again, so you might have something different depending on your resolution and so forth. And so 7.1 centimeters corresponds to a magnitude of 1. And so what I really want is I want the magnitude of the reflection coefficient at point P, not P prime. So what I do then is I measure the distance from O to P. And so when I did that by hand, I got 2.5 centimeters approximately. And so I set up a proportion then, because this thing is drawn to scale. I say, well, the magnitude of the reflection coefficient I'm looking for at P is to 1, which is at p prime, as 2.5 centimeters is to 7.1 centimeters. Because again, those are the measurements that I took. So 7.1 corresponds to a magnitude of 1. And so I solve this and I get the magnitude of the reflection coefficient at point P then is 0.352. So we also need the angle. The angle is easy. The angle of the reflection coefficient at point P is actually just given by the scale here. So you'll find again the angle by drawing this this dotted red line, and the angle looks to me about 55 degrees approximately. So that's this angle that I've also labeled it here, about 55 degrees. And so the reflection, now we have the magnitude and the angle of the reflection coefficient at point P. And so I can write my reflection coefficient as 0.352, angle 55 degrees, and I can use Euler's formula to put this in rectangular form, 0.202 plus j 0.288, and that is the reflection coefficient. Now for the VSWR, the voltage standing wave ratio, I just recall that that's 1 plus the magnitude of the reflection coefficient divided by 1 minus the magnitude of the reflection coefficient. So we've already got the magnitude of the reflection coefficient is 0.352 approximately. So this is just kind of a plug and chug, and just to illustrate that you can get the VSWR from the Smith chart, and that's 2.09 in this case. Alright, so now to answer part C. C was find the input impedance in this situation. So this is going to depend on the wavelength of our wave, of our generator's wave, source's wave. And so we can get that by noting that the wavelength times the frequency is the speed of the wave, in other words, the wavelength is the speed divided by the frequency, all of which were given. So this is the speed is 0.6 times the speed of light, which is 3 times 10 to the 8th, divided by the frequency, and the frequency we're told is 2 megahertz, or 2 times 10 to the 6th. And so when you take, of course, meters per second and you divide it by per second, you get meters. 90 meters in this case the wavelength is. And so we're going to get the length of the line in units of wavelength. So we're told that the length of the line is 30 meters from source to load, and so that's 1/3 wavelength, right? Because again, the wavelength is 90 meters, so 1/3 of 90 is 30. And so if you recall from our the previous video, the lambda over 2, the wavelength over 2 corresponds to 360 degrees. Okay, we mentioned that about the tangent and so forth. So if I go all the way around the circle, the Smith chart, I've gone lambda over 2. And so lambda over 3, which is what we're dealing with here, 1/3 lambda, you can set up a proportion, and you find that lambda over 3 corresponds to 240 degrees. So the proportion here would be lambda over 2 is to 360, as lambda over 3 is to x, and you solve for x, and you get 240 degrees. So what we're going to do, and I'll come back up here to the Smith chart, so we're going to take point P, and we're going to rotate towards the source, right? Because we want to know what impedance does the source see. So here's the impedance at the load, point P. Now we're going to move towards the source, so we're going to go clockwise. 240 degrees the source is away. So we're going to rotate this thing, our point, 240 degrees approximately. So we know this is 55 degrees, and we know a half a circle is 180 degrees, right? And so that puts us a little bit more into the inductance reactance over here, inductive reactance. And so that's about here, point G. And remember, this is all approximate, point G. So so I can read off the location of point G, and it looks like we're on the R circle of 0.55, and we're at the X circle of what is this guy? This is about 0.05, right? Because 0.01 is this line here. So we're at about 0.05. So let me come back down here. And so we find that the normalized impedance is just what I said here. Z in is 0.55 plus J 0.05. So again, remember that's in the normal coordinate system. So we have to unnormalize it this time, which means we multiply by the characteristic impedance of the line, which was 50. So when I do that multiplication, I get the input impedance is 27.5 plus J 2.5 ohms, which is the answer. Now, I just want to say a couple things about the Smith chart and its usefulness. So you might be a little skeptical about, you know, why would I need to do this? Um, because actually you can calculate all these things exactly with the information that was given. The point of doing this though is that for RF engineers, radio frequency engineers, what they do when they're constructing something, they actually have this oscilloscope, an oscilloscope that displays the Smith chart. And so what they do is they probe the line, they move around the line to get the impedance exactly where they want, right? Instead of measuring these things and calculating them, they actually put it into practice. So they'll be probing the line, and they'll see the point on the oscilloscope, this point P, move around as the engineer moves around the line. And so once you get to the actual input impedance that you want, you're at that location, and that's where you should connect the source.